The planets. A deep tour of our solar system. Chapter 1. Worlds in Motion. Look up at the night sky, and among the thousands of stars, a few points of light shine differently. They do not twinkle like stars do. They glow with a steady light, and if you watch them night after night, you will see them move against the background of fixed stars. These are the planets, from the Greek word meaning wanderers, worlds like our own orbiting the sun. For most of human history, we knew only 5 planets beyond Earth: Mercury, Venus, Mars, Jupiter, and Saturn, visible to the naked eye. Ancient astronomers tracked their motions across the sky, recognizing them as different from stars, though not understanding what they truly were. Some thought they were lights attached to crystalline spheres. Others believed they were gods or divine messengers. It was not until the early 1600s, when Galileo turned his telescope toward the heavens, that we began to understand planets as worlds. He saw mountains and valleys on the moon, proving it was a place, not just a light. He saw full moons orbiting Jupiter, proving that not everything circled Earth. And he saw phases of Venus, proving it orbited the Sun, not Earth. Over the following centuries, our understanding deepened. We discovered that planets are worlds, each unique, each shaped by the same physical laws that govern our own planet. We discovered Uranus in 1781, the first planet found using a telescope. We discovered Neptune in 1846 through mathematical prediction, calculating where it must be based on its gravitational effects on Uranus. And we discovered countless smaller worlds, asteroids, comets, and eventually, in the 20th century, Pluto and the other dwarf planets beyond Neptune. Today we know that our solar system contains 8 major planets, divided into 2 distinct groups. The inner 4, Mercury, Venus, Earth, and Mars, are terrestrial planets, rocky worlds with solid surfaces, relatively small in size. The outer 4, Jupiter, Saturn, Uranus, and Neptune, are giant planets, massive worlds composed primarily of gas and ice, with no solid surfaces to stand on. Between these 2 groups lies the asteroid belt, a region of rocky debris that never coalesced into a planet, prevented from doing so by Jupiter's powerful gravity. And beyond Neptune lies the Kuiper belt, a vast region of icy bodies including Pluto, remnants from the solar system's formation billions of years ago. But before we visit these worlds, we must understand where they came from. How did the planets form? Why are they so different from each other? The answer takes us back 4.6 billion years, to a time when the solar system was being born. The Sun formed from a collapsing cloud of gas and dust, as we explored in our journey through stellar evolution. But not all of the cloud fell into the Sun. The rotation of the cloud caused some material to flatten into a disk surrounding the young star, a protoplanetary disk. This disk contained about 1 to 2% of the total mass, but that small fraction was enough to build the planets. In the hot inner regions of this disk, close to the young Sun, only materials with high melting points could exist as solids. Silicate minerals, iron, and other metals condensed into tiny grains of dust. These grains collided and stuck together through electrostatic forces, gradually growing larger. Pebbles became boulders, boulders became mountain-sized objects called planetesimals, and planetesimals collided to form planetary embryos. This process, called accretion, continued over millions of years. The largest embryos had the strongest gravity and grew fastest, sweeping up nearby material and eventually becoming the terrestrial planets. Collisions were frequent and violent. The young Earth was struck by a Mars-sized object, and the debris from that impact formed the Moon. Mercury may have lost much of its rocky mantle in a similar collision, leaving it with an unusually large iron core. In the outer solar system, beyond the frost line where water could freeze, the conditions were different. Here, ice grains were far more abundant than rock and metal. The planetary embryos that formed in this region grew much larger, accumulating not just rock and ice, but also capturing vast amounts of hydrogen and helium gas from the surrounding disk. These became the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. Jupiter formed first and grew to immense size, containing more mass than all the other planets combined. Its powerful gravity stirred the asteroid belt, preventing the material there from forming a planet. It also scattered icy bodies inward and outward, creating the comets that still occasionally visit the inner solar system and populating the distant Oort cloud. The giant planets did not form where we see them today. Early in the solar system's history, they migrated, moving inward or outward as they exchanged angular momentum with the disk and with smaller bodies. Jupiter may have migrated inward and then outward again. Neptune likely formed closer to the Sun and migrated outward to its current position, scattering objects into the Kuiper belt as it went. This migration had profound effects. It may have scattered asteroids and comets into the inner solar system in an event called the Late Heavy Bombardment, about 4 billion years ago, peppering the young terrestrial planets with impacts. Some of these impacts may have delivered water and organic molecules to Earth, possibly providing the raw materials for life. Over time, the disk dissipated. The Sun's radiation and stellar wind pushed away the remaining gas. Collisions between planetesimals became less frequent as the largest bodies had swept up most of the available material. What remained was the solar system we see today: 8 major planets, countless smaller bodies, all orbiting the Sun in a dance that has continued for billions of years. The planets are not static. They continue to evolve, though slowly. Venus may once have had oceans but suffered a runaway greenhouse effect. Mars likely had a thicker atmosphere and liquid water on its surface, but lost most of its atmosphere over billions of years. Earth continues to be reshaped by plate tectonics, the only terrestrial planet where this process still operates vigorously. The giant planets have storms that last for centuries, atmospheric patterns that shift and change, and moons that may harbor subsurface oceans. Each planet is a world unto itself, shaped by its distance from the Sun, its composition, its size, and its history. By studying the planets, we learn about the processes that shaped our own world. By comparing them, we understand why Earth became habitable while Venus became hell and Mars became cold and dry. Tonight, we will visit each of these worlds in turn. We will start close to the Sun, with scorched Mercury, and journey outward through the solar system, past Venus, Earth, and Mars, through the asteroid belt, to the giant planets Jupiter and Saturn, then to the distant ice giants Uranus and Neptune, and finally to the edge of the solar system, where the Sun's influence fades and the realm of interstellar space begins. This is a journey across billions of kilometers, from worlds where lead melts in the sunlight to worlds where the air itself freezes. It is a journey through time, to see the remnants of planetary formation preserved in ancient, cratered surfaces, and to witness worlds still active, still changing. And it is a journey that reminds us of Earth's place in the solar system, one world among many, yet unique in its ability to support life. Let us begin our journey with the innermost planet, the small, swift world that races around the Sun faster than any other, Mercury. Chapter 2. Mercury, the Scorched World. Mercury is the closest planet to the Sun, orbiting at an average distance of about 58 million kilometers. It is also the smallest of the 8 major planets, only slightly larger than Earth's moon, with a diameter of about 4,900 kilometers. From its surface, the Sun appears 3 times larger than it does from Earth, and the intensity of sunlight is 7 times greater. This proximity to the Sun creates extreme conditions. Mercury has the most extreme temperature variation of any planet in the solar system. On the side facing the Sun, surface temperatures can reach 427 degrees Celsius, hot enough to melt lead and zinc. On the night side, temperatures plunge to minus 173 degrees Celsius, a swing of 600 degrees. This extreme variation occurs because Mercury has almost no atmosphere to distribute heat. The planet's gravity is too weak, and the solar wind too strong, to retain any significant atmosphere. What little gas exists around Mercury is constantly being replenished by the solar wind and by particles ejected from the surface by meteorite impacts, only to be lost to space almost immediately. Without an atmosphere, there is no weather, no wind, no erosion except from meteorite impacts. The surface of Mercury is ancient, heavily cratered, a record of billions of years of bombardment preserved in the airless environment. Some of these craters are enormous. The Hellish Basin, one of the largest impact features in the solar system, is about 1,500 kilometers across, formed by an asteroid or comet impact billions of years ago. The impact that created Hellish was so powerful that it sent shockwaves through the entire planet. On the opposite side of Mercury, directly across from Hellish, the surface is broken into strange, hilly terrain, apparently created when seismic waves from the impact converged and disrupted the crust. This is one of the few places in the solar system where we can see the effect of a giant impact on the opposite side of a world. Despite the intense heat during the day, Mercury has water ice. This seems impossible on a world so close to the Sun, but the ice exists in permanently shadowed craters at the poles. Because Mercury's axis is nearly perpendicular to its orbital plane, with almost no tilt, the Sun never rises high above the horizon at the poles. Deep craters in these regions never see sunlight and remain perpetually frozen, with temperatures cold enough to trap water ice and other volatiles delivered by comets. Radar observations from Earth and measurements by spacecraft have confirmed the presence of ice in these polar craters, perhaps meters thick in places. Some of this ice may be billions of years old, delivered by comet impacts in the early solar system and preserved in these cold traps ever since. Future missions or human explorers might use this ice as a resource, despite Mercury's harsh environment. Mercury's internal structure is unusual. The planet has an enormous iron core, about 3,600 kilometers in diameter, taking up about 75% of the planet's radius and over 60% of its mass. This is a much larger core fraction than any other planet. Earth's core, for comparison, takes up about 55% of the planet's radius, but only about 30% of its mass. Why does Mercury have such a large core? One possibility is that Mercury formed from material that was naturally rich in iron. Another possibility is that Mercury once had a much thicker rocky mantle, but a giant impact early in its history stripped away much of this mantle, leaving the iron core disproportionately large. Evidence from spacecraft suggests the second scenario may be correct, but the question is not fully settled. The iron core is not entirely solid. Mercury has a weak but measurable magnetic field, about 1% the strength of Earth's field, indicating that at least part of the core is liquid and convecting, generating the field through dynamo action. This is surprising for such a small planet. Scientists expected Mercury to have cooled and solidified long ago, but the magnetic field suggests ongoing activity in the interior. Mercury's rotation is unusual. It does not rotate once per orbit, as the Moon does around Earth. Instead, it rotates 3 times for every 2 orbits around the Sun, a 3-to-2 spin-orbit resonance. This means that a day on Mercury, from noon to noon, is actually 176 Earth days, exactly 2 Mercury years. Because of this resonance, certain longitudes on Mercury always face the Sun at perihelion, the point in the orbit closest to the Sun, creating hot poles where temperatures are highest. This resonance is not arbitrary. It results from the eccentricity of Mercury's orbit, which is more elliptical than any other planet except Pluto. At perihelion, Mercury is about 46 million kilometers from the Sun. At aphelion, it is about 70 million kilometers away. This variation in distance, combined with the tidal forces from the Sun, locked Mercury into its 3-to-2 resonance billions of years ago. Mercury has been visited by 2 spacecraft. Mariner 10 flew past 3 times in 1974 and 1975, imaging about 45% of the surface and discovering the magnetic field. More recently, the Messenger spacecraft orbited Mercury from 2011 to 2015, mapping the entire surface, measuring the composition, confirming water ice at the poles, and refining our understanding of the planet's interior and magnetic field. Messenger revealed that Mercury's surface is more diverse than previously thought. In addition to heavily cratered terrain, there are smooth plains, possibly created by ancient volcanic eruptions. There are scarps, long cliffs hundreds of kilometers long, formed as the planet cooled and contracted, wrinkling its crust like a drying apple. And there are unusual hollows, shallow depressions with bright, reflective flaws, possibly formed by the sublimation of volatile materials under intense solar radiation. Currently, the BepiColombo mission, a joint effort by the European Space Agency and the Japan Aerospace Exploration Agency, is on its way to Mercury. It will arrive in the mid-2020s and consists of 2 orbiters that will study Mercury's surface, interior, magnetic field, and tenuous atmosphere in unprecedented detail. These observations may finally answer lingering questions about Mercury's formation and evolution. Mercury's proximity to the Sun has made it difficult to study. Telescopes on Earth can only observe it during twilight, when it is low on the horizon. Spacecraft must contend with the intense heat and radiation near the Sun, requiring special thermal protection and complex orbits to slow down enough to be captured by Mercury's weak gravity. Yet despite these challenges, Mercury is a world worth studying. It is a world of extremes, a planet that has been battered and heated and shaped by forces that would destroy any life. Yet it endures, a small rocky sphere racing around the Sun every 88 days, its surface a testament to 4.5 billion years of solar system history. And in its polar craters, hidden in permanent shadow, ice waits, a reminder that even in the most unlikely places, water, the key to life as we know it, can be found. As we leave Mercury behind and journey outward, the next world we encounter could not be more different. Where Mercury has no atmosphere, Our next destination has an atmosphere so thick and oppressive that it has trapped enough heat to turn the planet into an inferno. We travel now to Venus, Earth's twin in size but its opposite in nearly every other way. Chapter 3. Venus, Earth's hellish twin. Venus is the second planet from the Sun, orbiting at an average distance of about 108 million kilometers. It is almost identical to Earth in size and mass, with a diameter of about 12,100 kilometers, only about 650 kilometers smaller than Earth. For this reason, Venus is often called Earth's twin or sister planet. But any similarity ends with size. Venus is the hottest planet in the solar system, despite being nearly twice as far from the Sun as Mercury. The surface temperature on Venus is a uniform 462 degrees Celsius, day and night, at the equator and at the poles. This is hot enough to melt lead, hot enough that spacecraft landers have survived on the surface for only an hour or two before succumbing to the extreme heat. This heat is not caused by proximity to the Sun. It is caused by the atmosphere. Venus has the thickest atmosphere of any terrestrial planet, with a surface pressure 92 times that of Earth's, equivalent to the pressure experienced 1 kilometer beneath Earth's oceans. This atmosphere is composed of 96% carbon dioxide, with clouds of sulfuric acid in the upper atmosphere. The carbon dioxide creates a runaway greenhouse effect. Sunlight penetrates the atmosphere and warms the surface. The surface radiates heat as infrared radiation, but the carbon dioxide absorbs this infrared, trapping the heat and warming the planet further. More heat means more carbon dioxide released from rocks, which traps even more heat, creating a feedback loop that has made Venus the hottest world in the solar system. This was not always the case. Venus likely had liquid water on its surface billions of years ago, when the Sun was cooler and the planet was forming. But as the Sun gradually brightened over its lifetime, temperatures on Venus rose. Water began to evaporate, and water vapor, itself a greenhouse gas, trapped more heat, causing more evaporation. Eventually, all the water was in the atmosphere. High in the atmosphere, solar ultraviolet light broke apart the water molecules. Hydrogen, being light, escaped to space. Oxygen reacted with rocks or was also lost to space. Over hundreds of millions of years, Venus lost its water entirely, leaving only the thick carbon dioxide atmosphere we see today. This is the runaway greenhouse effect, and it is a warning for what could happen to a planet if greenhouse gases are not controlled. The surface of Venus is hidden beneath the clouds. From space, Venus appears as a featureless white sphere, the sunlight reflecting off the sulfuric acid clouds that perpetually cover the planet. For centuries, we could only speculate about what lay beneath those clouds. Some imagined a tropical paradise, warm and wet. Others thought it might be a desert or an ocean-covered world. It was not until the 1960s and 70s, when Soviet Venera spacecraft descended through the atmosphere and landed on the surface, that we learned the truth. Venus is a hellish landscape of volcanic plains, mountains, and highland regions, baked to lead-melting temperatures under a crushing atmosphere. Radar imaging from spacecraft, particularly the Magellan mission in the early 1990s, mapped the entire surface of Venus in detail. The surface is relatively young, geologically speaking, with an average age of about 500 million years. This suggests that massive volcanic resurfacing occurred relatively recently, covering the older, more heavily cratered terrain with fresh lava flows. Venus has thousands of volcanoes, more than any other planet. Many are shield volcanoes, broad and gently sloping, similar to those in Hawaii but much larger. The largest, Mount Mons, rises about 8 kilometers above the surrounding plains. There are also features unique to Venus, such as pancake domes, circular mounds formed by the eruption of very viscous lava, and coronae, large circular features possibly created by upwelling mantle material that warped the crust. The surface shows evidence of tectonic activity, though not plate tectonics like on Earth. There are rift valleys, mountain ranges, and deformed terrain, suggesting that the crust has been pulled, compressed, and folded by forces in the interior. But there are no moving plates, no subduction zones. The crust appears to be a single, rigid shell, with volcanism and deformation occurring through other mechanisms. Why Venus lacks plate tectonics is uncertain. It may be related to the lack of water, which on Earth helps lubricate the crust and allows plates to move. Or it may be related to Venus's high surface temperature, which makes the crust more plastic and less likely to break into rigid plates. Whatever the reason, the absence of plate tectonics has profound implications for Venus's geology and climate. On Earth, plate tectonics plays a crucial role in regulating carbon dioxide levels. Volcanoes release carbon dioxide into the atmosphere, but weathering of rocks and the formation of carbonate minerals remove it, locking it into the crust. This carbon is eventually subducted and recycled through the mantle. On Venus, without plate tectonics, this cycle does not operate. Carbon dioxide accumulates in the atmosphere, contributing to the runaway greenhouse effect. Venus's rotation is another oddity. It rotates very slowly, taking 243 Earth days to complete one rotation. Even more strangely, it rotates backward, in the opposite direction to its orbit and to the rotation of most other planets. This retrograde rotation means that on Venus, the Sun rises in the west and sets in the east, though with a day longer than a year, a Venusian day is a strange concept. The cause of this retrograde rotation is unknown. One possibility is that Venus was struck by a massive object early in its history, and the impact flipped its rotation. Another possibility is that tidal forces from the Sun and the thick atmosphere have gradually reversed its rotation over billions of years. The question remains open, one of the many mysteries of Venus. The upper atmosphere of Venus is more dynamic than the surface. The clouds form in layers between about 45 and 70 kilometers altitude, where temperatures are more Earth-like, around 0 to 50 degrees Celsius. The clouds circle the planet in only 4 Earth days, driven by powerful winds at high altitude, a phenomenon called superrotation. Why the atmosphere rotates so much faster than the planet is not fully understood, but it involves complex interactions between the clouds, the solar heating, and the planet's slow rotation. The clouds are made of sulfuric acid, formed when sulfur dioxide from volcanic eruptions reacts with water vapor high in the atmosphere. These clouds are so reflective that Venus is the third brightest object in Earth's sky, after the Sun and Moon. To the naked eye, Venus appears as a brilliant white star, visible in the morning or evening, which is why ancient peoples called it both the morning star and the evening star before realizing it was the same object. Despite the hellish conditions, Venus has been explored by numerous spacecraft. The Soviet Union sent over 20 missions to Venus, including landers that successfully transmitted data from the surface, an extraordinary engineering achievement given the heat and pressure. The United States sent the Pioneer Venus and Magellan missions, which mapped the planet and studied its atmosphere. More recently, the European Space Agency's Venus Express and Japan's Akatsuki have studied the atmosphere from orbit. Future missions are planned. NASA's Veritas and Da Vinci missions aim to study Venus's surface and atmosphere in detail, mapping minerals and analyzing the composition of the atmosphere as it descends. The European Space Agency's Envision will also study Venus from orbit. These missions may help answer key questions. Is Venus still volcanically active today? Why did it lose its water? Could it have harbored life in the past, when it was cooler and possibly had oceans? That last question is intriguing. If Venus once had liquid water, it might have been habitable billions of years ago, before the runaway greenhouse effect took hold. Life, if it arose, would have been extinguished when the oceans evaporated. But some scientists have speculated that life might persist in the upper atmosphere, where temperatures and pressures are more moderate. The clouds are acidic, but some Earth organisms thrive in acidic conditions. Recent detections of phosphine gas in Venus's atmosphere, a potential biosignature, have sparked debate, though the findings are controversial. Venus is a cautionary tale. It shows how a planet similar to Earth in size and composition can become uninhabitable through a runaway greenhouse effect. It demonstrates the importance of understanding climate and how greenhouse gases can trap heat. And it reminds us that Earth's habitability is not guaranteed, that we live on a planet in a delicate balance that could, under the wrong conditions, shift to something very different. As we leave Venus behind and continue our journey outward, we come to the third planet from the Sun, the world we know best, the only planet we know for certain harbors life. We come home, to Earth. Chapter 4. Earth, the Blue Marble. We have traveled through the inner solar system, past scorched Mercury and hellish Venus, and now we arrive at a world unlike any other we know. From space, it appears as a blue and white sphere, with swirls of clouds, vast oceans, and brown and green continents. This is Earth, the third planet from the Sun, and the only world we know for certain harbors life. Earth orbits the Sun at an average distance of about 150 million kilometers, a distance we call 1 astronomical unit, or AU. This distance defines a region around the Sun called the habitable zone, where temperatures are just right for liquid water to exist on a planet's surface. Too close, like Venus, and water evaporates. Too far, like Mars, and water freezes. Earth sits in the middle, in the Goldilocks zone, where conditions are just right. But distance from the Sun is not the only factor that makes Earth habitable. Earth has a substantial atmosphere, thick enough to trap heat and moderate temperatures, but not so thick that it creates a runaway greenhouse effect like Venus. The atmosphere is composed primarily of nitrogen, about 78%, and oxygen, about 21%, with trace amounts of argon, carbon dioxide, water vapor, and other gases. The oxygen in Earth's atmosphere is remarkable. It is highly reactive and should not exist in large quantities unless something is constantly replenishing it. That something is life. Photosynthetic organisms, from cyanobacteria to plants, produce oxygen as a byproduct of converting carbon dioxide and water into sugars using sunlight. Without life, Earth's atmosphere would have little or no free oxygen, more like the atmospheres of Mars or Venus. Earth's atmosphere serves multiple vital functions. It traps heat through the greenhouse effect, keeping the planet warm enough for liquid water. It protects the surface from harmful ultraviolet radiation through the ozone layer, a region in the stratosphere where ozone molecules absorb UV light. It creates weather, distributing heat and moisture around the planet through winds, storms, and ocean currents. And it allows us to breathe, providing the oxygen that most complex life requires. About 71% of Earth's surface is covered by liquid water, collected in vast oceans. These oceans contain about 97% of all water on Earth. The remaining 3% is fresh water, found in ice caps, glacier, lakes, rivers, groundwater, and the atmosphere. Water is essential for life as we know it, serving as a solvent for biochemical reactions and helping regulate temperature. The oceans are not uniform. They have currents, driven by wind, temperature differences, and the rotation of the Earth. Warm water flows from the equator toward the poles, while cold water flows from the poles toward the equator, distributing heat and moderating climate. The Gulf Stream, for example, carries warm water from the Gulf of Mexico to the North Atlantic, making Europe warmer than it would otherwise be at its latitude. Earth's surface is divided into continents and ocean basins, but these are not permanent features. Earth is the only terrestrial planet with active plate tectonics, where the crust is broken into large plates that move slowly over the mantle beneath. These plates can collide, forming mountain ranges like the Himalayas. They can pull apart, creating rift valleys and new ocean floor. And they can slide past each other, causing earthquakes. Plate tectonics is driven by heat from Earth's interior, generated by radioactive decay and residual heat from the planet's formation. Hot mantle material rises, cools, and sinks in convection cells, dragging the plates along. This process recycles the crust, subducting old ocean floor and creating new crust at mid-ocean ridges. It also plays a crucial role in regulating climate by recycling carbon dioxide through volcanic eruptions and the weathering of rocks. Earth has a strong magnetic field, generated by a dynamo in its liquid iron outer core. The core is kept liquid by the heat from radioactive decay and the slow cooling of the planet. Convection in the liquid core creates electrical currents, which generate the magnetic field. This field extends tens of thousands of kilometers into space, forming the magnetosphere, which deflects the solar wind and protects Earth's atmosphere from being stripped away. Without this magnetic field, Earth might have lost much of its atmosphere over billions of years, as Mars did. The magnetosphere also protects life from harmful charged particles from space. When these particles do enter the atmosphere near the poles, they create auroras, the beautiful northern and southern lights visible at high latitudes. Earth's axial tilt, about 23.5 degrees, creates seasons. As Earth orbits the Sun, different parts of the planet receive more or less direct sunlight during different times of the year. When the northern hemisphere is tilted toward the Sun, it experiences summer, while the southern hemisphere experiences winter, and vice versa. This tilt, stabilized by the gravitational influence of the Moon, has remained relatively constant over Earth's history, providing a stable climate conducive to life. The Moon itself plays a crucial role in Earth's habitability. Its gravitational pull creates tides in Earth's oceans, mixing nutrients and creating intertidal zones where life thrives. The tides also slow Earth's rotation gradually over millions of years. Early in Earth's history, days were much shorter, perhaps only 6 hours long. Over billions of years, tidal friction has lengthened the day to 24 hours. The Moon also stabilizes Earth's axial tilt. Without the Moon, Earth's tilt would vary chaotically over millions of years due to gravitational perturbations from other planets, potentially causing extreme climate swings that could hinder the development of complex life. The Moon, formed from debris after a giant impact early in Earth's history, has been a companion and stabilizer for over 4 billion years. Earth's geology is diverse. There are mountain ranges, valleys, plains, deserts, and forests. There are active volcanoes, like those in the Ring of Fire around the Pacific Ocean, and dormant ones, like Mount Kilimanjaro in Africa. There are deep ocean trenches, like the Mariana Trench, which reaches nearly 11 kilometers below sea level. And there are vast continental shields, ancient stable regions of crust that have existed for billions of years. Life on Earth has transformed the planet. Photosynthetic organisms created the oxygen-rich atmosphere about 2.5 billion years ago in an event called the Great Oxygenation Event. Plants and other organisms have shaped the landscape, creating soil, forests, and grasslands. Coral reefs, built by tiny organisms, are among the largest structures created by life. And humans, in just a few thousand years, have reshaped much of the planet's surface. Earth is not static. The climate has varied over its history, from ice ages where glacier covered much of the continents to warm periods where there was little or no ice. Sea levels have risen and fallen. Continents have drifted, collided, and broken apart. Mass extinctions have wiped out the majority of species multiple times, yet life has always recovered and diversified. Currently, Earth is in an interglacial period, a relatively warm phase between ice ages. But human activity is now influencing the climate, increasing atmospheric carbon dioxide concentrations and causing global temperatures to rise. Understanding Earth's climate, its history, and its future is one of the most important scientific challenges of our time. Seen from space, Earth is a fragile blue sphere, an oasis of life in the vast emptiness of space. Carl Sagan called it a pale blue dot, a reminder of how small and vulnerable our world is, and how precious. It is the only home we have ever known, the only place where we know life exists. Every human who has ever lived has lived on this planet, under the same sky, breathing the same air. Yet Earth is also a testament to the resilience and adaptability of life. For nearly 4 billion years, life has persisted through asteroid impacts, volcanic eruptions, ice ages, and mass extinctions. It has evolved from simple single-celled organisms to the incredible diversity we see today, from bacteria to blue whales, from algae to redwood trees. As we leave Earth and continue our journey outward, we carry with us an appreciation for how special our world is. How many factors must align to create a habitable planet? The next world we encounter is Mars, a planet that once may have been similar to Earth, with liquid water and perhaps even life, but which today is cold, dry, and seemingly barren. Chapter 5. Mars, the Red Planet. Mars is the fourth planet from the Sun, orbiting at an average distance of about 228 million kilometers, about 1.5 times Earth's distance. It is a small planet, about half the diameter of Earth, with a mass only 11% that of our world. Yet Mars has captured human imagination like no other planet, as the most likely place beyond Earth where life might exist or might have existed in the past. From Earth, Mars appears as a reddish point of light in the night sky, earning it the nickname the Red Planet. This red color comes from iron oxide, rust, covering much of the Martian surface. The planet's atmosphere, though thin, sometimes carries dust storms that can engulf the entire planet, intensifying the red appearance. The Martian atmosphere is very thin, with a surface pressure less than 1% that of Earth's, equivalent to the pressure at about 35 kilometers altitude in Earth's atmosphere. It is composed of 95% carbon dioxide, with small amounts of nitrogen, argon, oxygen, and water vapor. This thin atmosphere provides little greenhouse warming, and Mars is cold, with average temperatures around -60 degrees Celsius. Despite the cold and thin atmosphere, Mars shows clear evidence that liquid water flowed on its surface in the past. There are dry river valleys, ancient lake beds, and deltas where rivers once emptied into lakes or seas. Some of these features are billions of years old, dating to a period called the Noachian era, when Mars was warmer and wetter. How Mars lost most of its atmosphere and water is one of the key questions in planetary science. Mars is smaller than Earth and cooled faster, and its core may have solidified early in its history. Without a liquid core, Mars could not maintain a magnetic field. Without a magnetic field, the solar wind gradually stripped away much of the atmosphere over billions of years, a process we can observe happening today thanks to spacecraft like MAVEN. As the atmosphere thinned, liquid water could no longer exist on the surface. Some water evaporated and was lost to space. Some seeped into the ground and froze as permafrost or formed subsurface ice deposits. And some may exist today as briny liquid water beneath the surface, protected from evaporation by layers of soil and ice. Mars has polar ice caps, visible even through small telescopes from Earth. These caps are made of water ice and frozen carbon dioxide, or dry ice. In winter, carbon dioxide from the atmosphere freezes onto the poles, and the caps grow larger. In summer, the dry ice sublimes back into the atmosphere, and the caps shrink, leaving behind mostly water ice. The northern polar cap is larger and mostly water ice. The southern polar cap is smaller and contains more dry ice mixed with water ice. The surface of Mars is diverse and fascinating. There are vast plains, ancient highlands, and enormous volcanoes. Olympus Mons is the tallest volcano in the solar system, standing about 22 kilometers high, nearly 3 times the height of Mount Everest. It is a shield volcano, similar in shape to volcanoes in Hawaii but vastly larger. The volcano is so large that its base covers an area roughly the size of Arizona. Mars also has the solar system's largest canyon system, Valles Marineris, stretching about 4,000 kilometers along the equator, roughly 1/5 the circumference of Mars. It is up to 7 kilometers deep and 200 kilometers wide in places, making it 10 times longer and 5 times deeper than Earth's Grand Canyon. Valles Marineris may have formed from tectonic stresses as Mars cooled and its crust contracted, though its exact origin is still debated. The surface of Mars is heavily cratered in some regions, like the southern highlands, indicating ancient terrain billions of years old. Other regions, like the northern lowlands, have fewer craters and may have been resurfaced by lava flows or sediment deposition. The northern lowlands are also much lower in elevation than the southern highlands, a hemispheric dichotomy whose cause is uncertain. Some scientists think a giant impact may have created this difference early in Mars's history. Mars has dust storms, ranging from small dust devils that rovers have observed and even photographed themselves within, to planet-wide storms that can last for weeks or months. These storms are driven by temperature differences and winds in the thin atmosphere. When Mars is closest to the Sun in its elliptical orbit, the increased heating can trigger large storms. In 2018, a global dust storm caused the Opportunity rover to lose power and end its mission. Mars has two small moons, Phobos and Deimos, named after the companions of the Roman god of war. These moons are tiny, irregularly shaped, and heavily cratered. Phobos orbits very close to Mars, only about 6,000 kilometers above the surface, and completes an orbit in just 7.5 hours. It is gradually spiraling inward and will either crash into Mars or be torn apart by tidal forces in about 50 million years. Deimos orbits farther out and is even smaller, only about 15 kilometers across. Mars has been explored by more spacecraft than any planet other than Earth. Dozens of missions have been sent to Mars, though many failed, especially in the early years of space exploration. But the successes have been remarkable. Orbiters have mapped the entire surface in detail. Landers have studied the soil, rocks, and atmosphere. Rovers have driven across the surface, drilled into rocks, and analyzed their composition. The Viking landers in the 1970s were the first to successfully land on Mars and operate for extended periods, taking the first color images from the surface and conducting experiments to search for life. The results were inconclusive, and debate continues about their interpretation. More recently, rovers like Spirit, Opportunity, Curiosity, and Perseverance have transformed our understanding of Mars. Curiosity, which landed in Gale Crater in 2012, has found evidence that ancient Mars had the right chemical ingredients, liquid water, and energy sources that could have supported microbial life. Perseverance, which landed in Jezero Crater in 2021, is collecting rock samples that may one day be returned to Earth for detailed analysis. Mars is also home to the first successful helicopter on another planet. Ingenuity, a small drone that accompanied Perseverance, has made dozens of flights in the thin Martian atmosphere, demonstrating that powered flight is possible on Mars and scouting routes for the rover. The search for life on Mars is ongoing. Mars likely had habitable conditions billions of years ago, with liquid water, organic molecules, and energy sources. If life arose, it might have gone extinct when Mars lost its atmosphere and water. Or it might persist in subsurface environments, protected from the harsh surface conditions. Future missions will drill deeper and explore more diverse locations to search for biosignatures. Mars is also a target for human exploration. NASA and other space agencies are developing plans to send humans to Mars in the coming decades. The challenges are immense. The trip takes about 7 months one way, the environment is hostile, and astronauts would need to produce water, oxygen, and fuel on Mars to return. But the goal is achievable with current or near-future technology. Humans on Mars would face low gravity, about 38% of Earth's. They would need protection from radiation, as Mars has no magnetic field and a thin atmosphere. They would need habitats to maintain pressure and provide breathable air. And they would need to be self-sufficient, as resupply missions from Earth would be infrequent and expensive. But there are resources on Mars. Water ice is abundant at the poles and in subsurface deposits at lower latitudes. This ice can be melted for drinking water and split into hydrogen and oxygen for fuel and breathable air. The thin atmosphere, though mostly carbon dioxide, can be processed to produce oxygen and methane. Regolith, the Martian soil, can be used for construction, either as bulk material or processed into bricks. Some visionaries imagine eventually terraforming Mars, transforming it into a more Earth-like world with a thicker atmosphere, warmer temperatures, and liquid water on the surface. This would be a project spanning centuries or millennia, involving releasing greenhouse gases to warm the planet, melting the polar caps, and perhaps importing volatiles from comets or other sources. Whether this is desirable or ethical is a question for future generations. Mars is a world that once may have been habitable and might one day be inhabited. It is a world that holds clues to the history of water, climate, and possibly life in the solar system. And it is a world that, more than any other, represents humanity's next step outward from Earth, a stepping stone to becoming a multi-planetary species. As we leave Mars behind and continue our journey outward through the solar system, we enter a region very different from the terrestrial planets. We cross the asteroid belt, a vast zone of rocky debris that never coalesced into a planet, remnants of the solar system's formation scattered between Mars and Jupiter. Chapter 6. The Asteroid Belt. Debris between worlds. Between the orbits of Mars and Jupiter lies the asteroid belt, a region of space about 150 million kilometers wide, populated by millions of rocky bodies ranging in size from dust grains to objects hundreds of kilometers across. These are the asteroids, remnants of the protoplanetary disk that never assembled into a planet, prevented from doing so by the gravitational influence of Jupiter. The asteroid belt is not densely packed as science fiction sometimes portrays. The asteroids are spread over an enormous volume of space. If you were to fly a spacecraft through the asteroid belt, you would likely see no asteroids with the naked eye. They are too small and too far apart. Most of the time, the nearest asteroid would be millions of kilometers away. Spacecraft have traveled through the belt many times without incident. Despite the large number of asteroids, their total mass is small. If you could gather every object in the asteroid belt together, the combined mass would be about 4% the mass of the Moon, or about 6 times 10 to the 20 kilograms. More than half of this mass is contained in the 4 largest objects: Ceres, Vesta, Pallas, and Hygiea. Ceres is the largest object in the asteroid belt, and the only one massive enough to have pulled itself into a spherical shape under its own gravity. With a diameter of about 940 kilometers, Ceres is classified as a dwarf planet, the smallest in the solar system. It orbits the Sun every 4.6 years at an average distance of about 414 million kilometers. Ceres is a fascinating world. Observations from the Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a surface covered in craters, but also mysterious bright spots, particularly in a crater called a crater. These bright areas are deposits of sodium carbonate and other salts, left behind when briny water from beneath the surface erupted and evaporated. Ceres likely has a subsurface layer of water or brine beneath its rocky crust. In some ways, it resembles the icy moons of the outer solar system more than a typical asteroid. The discovery of organic molecules on Ceres and evidence of recent geological activity raises intriguing questions about whether it could have been or still be habitable in some way. Vesta is the second most massive object in the asteroid belt, but is not spherical. It has a diameter of about 525 kilometers and an irregular shape, with a massive impact basin at its south pole. This basin, called Silvia, is about 500 kilometers across and 19 kilometers deep, one of the largest impact craters relative to body size in the solar system. The impact that created Rear Sylvia nearly shattered Vesta, ejecting a huge amount of material into space. Some of this material has fallen to Earth as a particular type of meteorite called HED meteorites, which we can study in laboratories. Dawn also orbited Vesta and revealed a world with a differentiated interior, including a crust, mantle, and iron core, much like a terrestrial planet. Vesta is essentially a protoplanet, a body that was on its way to becoming a planet but whose growth was halted, likely by Jupiter's gravity preventing additional material from accreting. Studying Vesta gives us a glimpse into the early stages of planet formation, a snapshot of what Earth might have looked like in its first few million years. Most asteroids are much smaller than Ceres or Vesta. They are irregular chunks of rock and metal, tumbling through space, colliding occasionally and breaking into smaller fragments. Asteroids are classified by their composition and spectra. C-type or carbonaceous asteroids are dark and rich in carbon, making up about 75% of known asteroids. S-type or silicaceous asteroids are brighter and made of silicate rock and metal, making up about 17%. M-type or metallic asteroids are made primarily of iron and nickel. M-type asteroids are of particular interest for future resource exploitation. An asteroid made of pure iron and nickel could contain more metal than has been mined in all of human history. As space technology advances, mining asteroids for metals, water, and other resources may become feasible, providing materials for construction in space and reducing the need to launch everything from Earth. Some asteroids have orbits that bring them close to Earth. These near-Earth asteroids are monitored carefully, as a collision with Earth could cause significant damage. The asteroid that struck Earth 66 million years ago, causing the extinction of the dinosaurs, was likely about 10 kilometers across. An impact of that scale today would be catastrophic for human civilization. Fortunately, such large impacts are extremely rare, occurring only once every 100 million years or so. Smaller impacts are more frequent but less dangerous. Objects a few meters across enter Earth's atmosphere regularly, usually burning up and creating meteors or shooting stars. Larger objects, a few tens of meters across, can reach the ground, as happened in 2013 when a meteor exploded over Chelyabinsk, Russia, damaging buildings and injuring about 1,500 people. Efforts are underway to catalogue all near-Earth asteroids larger than 140 meters, the size that could cause regional devastation. If we find an asteroid on a collision course with Earth, we may be able to deflect it with sufficient warning. NASA's DART mission successfully demonstrated this in 2022, when a spacecraft intentionally crashed into the asteroid Dimorphos and changed its orbit. Asteroids are also of scientific interest as remnants of the early solar system. They have been largely unchanged for billions of years, preserving a record of the conditions in the protoplanetary disk. Meteorites, pieces of asteroids that have fallen to Earth, provide samples we can study in detail, learning about the composition, age, and processes that occurred in the early solar system. Some asteroids even contain organic molecules and amino acids, the building blocks of proteins. The carbonaceous chondrite meteorites are particularly rich in these materials. It is possible that impacts by asteroids and comets delivered organic molecules and water to the early Earth, providing the raw materials for life. The asteroid belt is a dynamic region. Asteroids collide, break apart, and occasionally are perturbed into new orbits by gravitational interactions with planets, especially Jupiter. Some asteroids are knocked out of the belt entirely, either falling into the inner solar system or being ejected outward. There are also asteroids beyond the main belt. The Trojan asteroids share Jupiter's orbit, clustered at stable points called Lagrange points ahead of and behind the planet. These Trojans are captured asteroids that have been trapped by the gravitational balance between Jupiter and the Sun. NASA's Lucy mission, launched in 2021, will visit several Trojan asteroids to study these distant remnants of planetary formation. As we leave the asteroid belt behind, we now enter the realm of the giant planets. The change is dramatic. The inner solar system is dominated by small, rocky worlds with solid surfaces. The outer solar system is dominated by massive gas and ice giants, planets many times the mass of Earth, with no solid surfaces, surrounded by rings and dozens of moons. The first and largest of these giants is Jupiter, king of the planets, a world so massive it contains more than twice the mass of all other planets combined. Let us now journey to this giant world. Chapter 7. Jupiter, King of the Planets. Jupiter is the fifth planet from the Sun, orbiting at an average distance of about 778 million kilometers, more than 5 times Earth's distance. It is the largest planet in the solar system, with a diameter of about 143,000 kilometers, over 11 times Earth's diameter. Jupiter is so large that all the other planets combined could fit inside it with room to spare. Jupiter is also the most massive planet, containing more than twice the mass of all other planets combined. Yet despite this enormous mass, about 318 times Earth's mass, Jupiter is not a solid world. It is a gas giant, composed primarily of hydrogen and helium, the same elements that make up the Sun and stars. If Jupiter had been about 75 times more massive, it would have ignited nuclear fusion in its core and become a star rather than a planet. From Earth, Jupiter is one of the brightest objects in the night sky, visible as a brilliant white point of light. Through even a small telescope, Jupiter's disk is visible, showing bands of clouds and sometimes the Great Red Spot, a massive storm that has raged for at least 350 years. Larger telescopes or spacecraft reveal an atmosphere of incredible complexity, with swirling storms, jet streams, and atmospheric features that evolve and change over days, weeks, and years. Jupiter's atmosphere is divided into bands parallel to the equator. The lighter bands are called zones, and the darker bands are called belts. Zones are regions of rising gas, where ammonia clouds form at high altitudes, creating the bright appearance. Belts are regions of sinking gas, where we see deeper into the atmosphere, revealing darker, warmer material below. These bands are created by powerful jet streams, winds that blow at hundreds of kilometers per hour. Jupiter rotates incredibly fast, completing one rotation in just under 10 hours, the fastest rotation of any planet. This rapid rotation, combined with convection and internal heat, creates the jet streams through a complex interplay of forces. The result is a banded appearance unlike anything seen on terrestrial planets. The Great Red Spot is Jupiter's most famous feature, an anticyclonic storm larger than Earth. It rotates counterclockwise in Jupiter's southern hemisphere, with winds at the edge exceeding 400 kilometers per hour. The storm's red color may come from complex organic molecules created by sunlight interacting with chemicals in the atmosphere, though the exact cause is still debated. The Great Red Spot has been observed for at least 350 years, first documented by observers in the 1600s. Over time, it has changed in size and shape. In the late 1800s, it was large enough to fit 3 Earths inside. Today, it is smaller, though still larger than Earth. Some scientists wonder if the storm will eventually dissipate, but for now, it remains a prominent feature, a testament to the stability of Jupiter's atmospheric dynamics. Jupiter has many other storms, some smaller, some large and long-lived. White ovals, smaller anticyclonic storms, appear and sometimes merge. Brown barges, regions of darker material, drift through the belts. Lightning has been observed in Jupiter's atmosphere, sometimes more powerful than lightning on Earth. And auroras, created when charged particles from Jupiter's magnetosphere strike the upper atmosphere near the poles, glow in ultraviolet and infrared light. Beneath the visible clouds lies an atmosphere of increasing pressure and temperature. As you descend, the hydrogen gas becomes denser and hotter. At about 1,000 kilometers depth, the pressure is so great that hydrogen transitions to a liquid state. At about 20,000 kilometers depth, the pressure exceeds 2 million times Earth's atmospheric pressure, and hydrogen becomes metallic, a state where it conducts electricity like a metal. This metallic hydrogen layer makes up most of Jupiter's interior and is responsible for Jupiter's powerful magnetic field. As Jupiter rotates, the metallic hydrogen convects and generates electrical currents, creating a dynamo that produces a magnetic field about 20,000 times stronger than Earth's. This field extends millions of kilometers into space, creating the largest structure in the solar system, Jupiter's magnetosphere. The magnetosphere traps charged particles from the solar wind and from Io, one of Jupiter's moons. These particles create intense radiation belts around Jupiter, far more dangerous than Earth's Van Allen belts. Spacecraft passing through the inner magnetosphere must be specially shielded, and the radiation is lethal to humans. The Europa Clipper mission, for example, will use highly elliptical orbits to minimize time spent in the most intense radiation regions. Jupiter's magnetosphere interacts dramatically with its moons, particularly Io. As Io orbits through Jupiter's magnetic field, electrical currents flow between the Moon and the planet, creating auroras at Jupiter's poles and stripping material from Io's volcanic atmosphere. This creates a torus of ionized gas, primarily sulfur and oxygen, that circles Jupiter along Io's orbit. At the center of Jupiter, beneath the metallic hydrogen, there may be a core of rock and ice, perhaps 10 to 20 times Earth's mass. But this core is not solid in the way we think of solid. The pressure is so extreme, tens of millions of times Earth's atmospheric pressure, and the temperature is so high, perhaps 35,000 degrees Celsius, that matter exists in exotic states we cannot replicate in laboratories. Jupiter emits more heat than it receives from the Sun. This internal heat, about 1.7 times the energy absorbed from sunlight, comes from 2 sources. One is residual heat from Jupiter's formation, the planet still slowly cooling after 4.6 billion years. The other is gravitational contraction. Jupiter is still very slowly shrinking, and the gravitational potential energy released by this contraction is converted to heat. This internal heat drives convection in Jupiter's atmosphere and interior, contributing to the weather and the powerful jet streams. It also means that Jupiter would have a temperature and atmospheric circulation even without the Sun, though of course it would be much colder and darker. Jupiter has at least 95 known moons, and more are discovered regularly. Most are small, irregular objects, likely captured asteroids or fragments from larger moons. But the four largest moons, discovered by Galileo in 1610, are worlds unto themselves. These are the Galilean moons, Io, Europa, Ganymede, and Callisto, each with unique characteristics and scientific interest, as we explored in detail in our journey through the moons of the solar system. Jupiter also has faint rings, discovered by the Voyager 1 spacecraft in 1979. These rings are made of dust and small particles, probably debris from meteorite impacts on Jupiter's small inner moons. The rings are much fainter than Saturn's and are not visible from Earth without powerful telescopes or spacecraft. Jupiter plays a crucial role in the solar system. Its enormous gravity influences the orbits of asteroids and comets, sometimes flinging them into the inner solar system or ejecting them entirely. This has led some to call Jupiter the solar system's vacuum cleaner or shield, protecting the inner planets from some impacts. The comet Shoemaker-Levy 9, which broke apart and collided with Jupiter in 1994, demonstrated this dramatically. If that comet had hit Earth, the consequences would have been catastrophic. Jupiter has been visited by multiple spacecraft. Pioneer 10 and 11 flew past in the 1970s, providing the first close-up images. Voyager 1 and 2 followed, revealing the complexity of Jupiter's atmosphere and discovering the rings. The Galileo spacecraft orbited Jupiter from 1995 to 2003, studying the planet, its magnetosphere, and its moons in detail, and dropping a probe into Jupiter's atmosphere. More recently, the Juno spacecraft has been orbiting Jupiter since 2016, studying its gravity field, magnetic field, and internal structure. Juno's measurements have revealed that Jupiter's core may be partially dissolved, mixed with the surrounding hydrogen, rather than being a distinct solid or liquid object. These findings are reshaping our understanding of how giant planets form and evolve. Jupiter is a world of superlatives. It is the largest, the most massive, the fastest rotating, and has the strongest magnetic field. Its storms are larger than planets. Its radiation belts could kill a human in minutes. Its gravitational influence shapes the entire solar system. And yet, for all its power and size, Jupiter is ultimately just a ball of gas, held together by its own gravity, slowly cooling and contracting over billions of years. As we leave Jupiter and continue our journey outward, we travel to a world that rivals Jupiter in beauty if not in size. We journey to the jewel of the solar system, the ringed planet that has inspired wonder since humans first pointed telescopes toward the heavens. We travel now to Saturn. Chapter 8. Saturn, Lord of the Rings. Saturn is the sixth planet from the Sun, orbiting at an average distance of about 1.4 billion kilometers, nearly twice as far as Jupiter. It is the second largest planet, with a diameter of about 120,000 kilometers, about 9.5 times Earth's diameter. Yet Saturn is less massive than Jupiter, containing only 95 times Earth's mass, about 30% of Jupiter's mass. This lower mass relative to its size gives Saturn the lowest density of any planet in the solar system. Saturn's average density is about 700 kilograms per cubic meter, less than the density of water, which is 1,000 kilograms per cubic meter. If you could find an ocean large enough, Saturn would float, though the experience would be messy, as Saturn has no solid surface. Like Jupiter, Saturn is a gas giant composed primarily of hydrogen and helium. Its internal structure is similar to Jupiter's, with an atmosphere of hydrogen and helium transitioning to liquid hydrogen, and then metallic hydrogen deep in the interior. Saturn also has a core of rock and ice at its center, though smaller relative to the planet's size than Jupiter's core. Saturn emits about 2.5 times as much energy as it receives from the Sun, even more than Jupiter relative to the solar input. This excess heat comes from gravitational contraction, and from a process unique to Saturn. Deep in Saturn's interior, helium is denser than hydrogen and slowly rains downward toward the core. This releases gravitational potential energy, which is converted to heat, warming the planet and contributing to its atmospheric circulation. Saturn rotates rapidly, completing one rotation in about 10.5 hours, only slightly slower than Jupiter. This rapid rotation creates a pronounced equatorial bulge. Saturn's equatorial diameter is about 10% larger than its polar diameter, making it the most oblate planet in the solar system. This shape is visible even in small telescopes. Saturn's atmosphere shows bands similar to Jupiter's, with zones and belts created by jet streams and convection. But Saturn's bands are more muted, less colorful than Jupiter's. The clouds are composed of ammonia ice crystals in the upper layers, with water and ammonia droplets deeper down. Hazes of hydrocarbons, formed by sunlight breaking apart methane, give Saturn a soft, golden appearance. Saturn has storms, though generally fewer and smaller than Jupiter's storms. However, about once per Saturn year, roughly every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, creating a bright white spot that can grow to encircle the entire planet. These great white spots are caused by convection bringing material from deep in the atmosphere to the surface, where it freezes into bright clouds. The most recent great white spot occurred in 2010 and 2011, observed in detail by the Cassini spacecraft. One of Saturn's most intriguing features is a hexagonal storm pattern at the North Pole. This hexagon is about 30,000 kilometers across, larger than Earth, and rotates with the planet. The hexagon is a jet stream, a meandering current created by the interplay of Saturn's rotation and atmospheric dynamics. Similar hexagonal patterns can be created in laboratory experiments with rotating fluids, but seeing one on a planetary scale is remarkable. Saturn has a magnetic field, though weaker than Jupiter's, only about 600 times stronger than Earth's. The field is unusual because it is almost perfectly aligned with Saturn's rotation axis, unlike Earth and Jupiter, where the magnetic and rotation axes are tilted relative to each other. This near-perfect alignment is still not fully understood and suggests something unique about the structure or dynamics of Saturn's interior. But Saturn's most spectacular feature, the feature that makes it instantly recognizable, is its ring system. Saturn's rings are the most extensive and beautiful in the solar system, visible from Earth through even small telescopes. They extend from about 7,000 kilometers above Saturn's equator to about 80,000 kilometers, spanning a distance greater than the diameter of the planet itself. Yet despite their enormous extent, the rings are incredibly thin. In most places, they are only about 10 meters thick, thinner than a sheet of paper if scaled to their width. This thinness makes the rings nearly disappear when viewed edge-on from Earth, an event that occurs roughly every 15 years as Saturn's axial tilt causes the rings to be seen from different angles. The rings are composed of countless particles of water ice, ranging in size from tiny grains smaller than sand to boulders several meters across. Each particle orbits Saturn independently, following its own elliptical path around the planet. The ring particles are not uniformly distributed, but are organized into distinct rings separated by gaps. The most prominent rings, visible from Earth, are designated A, B, and C, from outermost to innermost of the main rings. The B ring is the brightest and most opaque. The A ring is slightly dimmer. The C ring is fainter and more transparent. Between the A and B rings lies the Cassini division, a prominent gap about 4,800 kilometers wide, visible from Earth through telescopes and named after Giovanni Cassini, who discovered it in 1675. The gaps in the rings are not empty, but contain fewer particles than the rings themselves. They are created by gravitational resonances with Saturn's moons. Particles in these gaps have orbital periods that are simple fractions of the orbital periods of certain moons. These resonances cause repeated gravitational tugs that perturb the particles' orbits, clearing out the gaps over time. Some gaps contain small moons, called shepherd moons, which help confine the rings. Prometheus and Pandora, for example, orbit on either side of the narrow F ring, their gravity preventing ring particles from spreading too far. The F ring itself is complex, with braids and kinks created by interactions with these shepherd moons and with clumps of material in the ring. The rings are not permanent features. They are likely only about 100 million to a few hundred million years old, much younger than Saturn itself. The rings may have formed from a moon or large comet that wandered too close to Saturn and was torn apart by tidal forces, or from debris created by a collision between moons. Over time, the rings are being depleted, with material falling into Saturn or being lost to space. In perhaps 100 million years, Saturn may no longer have its magnificent rings. Saturn has at least 146 known moons, more than any other planet. Most are small, irregular objects, but several are large and scientifically fascinating. Titan, the largest, is bigger than the planet Mercury and has a thick atmosphere, making it unique among moons. Enceladus, though small, has geysers erupting from its south pole, indicating a subsurface ocean. These and other moons were explored in detail in our journey through the solar system's satellites. Saturn has been visited by 4 spacecraft. Pioneer 11 flew past in 1979, providing the first close-up images of the rings. Voyager 1 and 2 followed in 1980 and 1981, revealing the complexity of the rings and discovering new moons. But the most transformative mission was Cassini, which orbited Saturn from 2004 to 2017, making countless discoveries about the planet, its rings, and its moons. Cassini revealed that the rings are dynamic, with waves, spirals, and ephemeral features created by gravitational interactions with moons. It discovered geysers on Enceladus and lakes on Titan. It observed seasonal changes in Saturn's atmosphere and captured stunning images of the planet, its rings, and its moons. At the end of its mission, Cassini dove into Saturn's atmosphere, sending back data until it was destroyed, ensuring it would not contaminate any of Saturn's potentially habitable moons. Saturn is a world of grace and beauty, a giant planet adorned with the solar system's most spectacular rings. It is a reminder that the universe creates structures of incredible complexity and elegance, that physics and gravity can produce art. And it is a world that continues to surprise us, revealing new mysteries with each observation and each mission. As we leave Saturn behind and journey farther from the Sun, the solar system grows colder and darker. The next planet, Uranus, is so distant that sunlight is only about 1/400th as intense as on Earth. Here, in the cold outer reaches, we encounter the ice giants, planets very different from Jupiter and Saturn, worlds that challenge our understanding of planetary formation and evolution. Chapter 9. Uranus, the sideways planet. Uranus is the seventh planet from the Sun, orbiting at an average distance of about 2.9 billion kilometers, about 19 times Earth's distance. It is the third largest planet by diameter, about 51,000 kilometers across, roughly 4 times the diameter of Earth. Uranus takes 84 Earth years to complete one orbit around the Sun, moving slowly through the distant reaches of the solar system. Uranus is classified as an ice giant, a term that distinguishes it from the gas giants Jupiter and Saturn. While all 4 giant planets are composed mostly of hydrogen and helium, Uranus and Neptune have proportionally more water, methane, and ammonia, substances astronomers call ices, even though they are not frozen at the temperatures and pressures inside these planets. Uranus's interior likely consists of a small rocky core surrounded by an icy mantle of water, methane, and ammonia in various states, compressed by the enormous pressure. Above this lies an atmosphere of hydrogen and helium, much thinner relative to the planet's size than the atmospheres of Jupiter or Saturn. This different composition and structure are why Uranus is less massive than Saturn despite being larger in diameter than Neptune. From Earth, Uranus appears as a small, pale blue-green disk through telescopes. The color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green. Without methane, Uranus would appear white or gray like Jupiter and Saturn. The planet's appearance is bland compared to Jupiter or Saturn, with few visible features in most images. This apparent calmness is misleading. Uranus has an active atmosphere, with winds reaching speeds of up to 900 kilometers per hour. But the atmospheric features are subtle, often visible only in infrared or with image enhancement. Occasionally, bright clouds appear, created by convection bringing material from deeper layers to the surface where it condenses into ice crystals. The most remarkable feature of Uranus is its extreme axial tilt. While most planets rotate with their axes roughly perpendicular to their orbital planes, Uranus's axis is tilted 98 degrees. The planet is essentially lying on its side, rolling around the Sun like a ball rather than spinning like a top. This tilt means that Uranus's poles, rather than its equator, point toward the Sun at different times in its orbit. The consequences of this tilt are dramatic. Each pole experiences 42 years of continuous sunlight followed by 42 years of continuous darkness as Uranus orbits the Sun. During the summer solstice, one pole points directly at the Sun and receives constant sunlight, while the other pole is in complete darkness. During the winter solstice, the situation reverses. At the equinoxes, the Sun is above the equator, and the planet experiences more Earth-like day-night cycles. What caused this extreme tilt? The most likely explanation is a collision with an Earth-sized or larger object early in the solar system's history. Such an impact would have been catastrophic, potentially melting parts of Uranus and tilting its entire axis. Simulations show that a collision at the right angle and speed could produce Uranus's current tilt while leaving the planet mostly intact. This collision may also explain another peculiarity: Uranus's magnetic field. The field is tilted nearly 60 degrees from the rotation axis and offset from the planet's center. This is very different from Earth, Jupiter, or Saturn, where the magnetic field aligns more closely with the rotation axis. The offset and tilt suggest that the magnetic field is generated not in a core but in a shell of conductive material, possibly salty water or ionized ice, at mid-depths in the planet. Uranus has a faint ring system, discovered in 1977 when astronomers observed Uranus passing in front of a star and noticed brief dimming events before and after the planet itself blocked the star. These dimmings revealed the presence of narrow rings around Uranus. The Voyager 2 flyby in 1986 confirmed the rings and discovered additional ones. Uranus's rings are very different from Saturn's. They are narrow, dark, and contain little fine dust. The largest ring, the Epsilon ring, is only about 100 kilometers wide but nearly opaque. The rings are composed of rocks and ice chunks, possibly debris from shattered moons. Some rings have shepherd moons that help confine them, similar to Saturn's F ring. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are all ice rock mixtures, similar in composition to Saturn's moons but located much farther from the Sun. Miranda, the smallest of the 5 major moons, is particularly bizarre. Its surface is a patchwork of different terrains, with ancient cratered regions adjacent to grooved and ridged areas. One of the most striking features is Verona Rupes, a cliff about 20 kilometers high, the tallest known cliff in the solar system. How Miranda came to have such a diverse and fractured surface is unclear, but it may have been shattered by an impact and reassembled, or it may have experienced intense tidal heating in the past. Uranus is a cold world. The upper atmosphere has temperatures around -224 degrees Celsius, making it the coldest planetary atmosphere in the solar system. This is colder even than Neptune, despite Uranus being closer to the Sun. The reason is that Uranus emits very little internal heat, unlike Jupiter, Saturn, and Neptune. It radiates only about as much heat as it receives from the Sun, with no significant excess. Why Uranus emits so little internal heat is a mystery. One possibility is that the giant impact that tilted Uranus also disrupted its interior, preventing convection and trapping heat deep inside. Another possibility is that the interior has stratified, with layers of different compositions that do not mix, inhibiting heat transport. Without convection bringing heat to the surface, Uranus remains colder than it otherwise would be. Uranus was discovered in 1781 by William Herschel, the first planet discovered using a telescope. Herschel initially thought it was a comet, but observations over the following months revealed that it moved in a circular orbit beyond Saturn. This discovery doubled the known size of the solar system and demonstrated that there were worlds beyond those known to the ancients. Uranus has been visited by only one spacecraft, Voyager 2, which flew past in January 1986. Voyager revealed the rings, discovered 10 new moons, measured the magnetic field, and captured the only close-up images of Uranus and its moons we have. Nearly 40 years later, Uranus remains largely unexplored, with much still to learn. Proposed missions to Uranus or Neptune are periodically discussed. An orbiter would transform our understanding, studying the atmosphere, interior, rings, and moons over multiple years. But such a mission faces challenges. The journey takes over a decade, and operating in the cold, distant environment requires careful engineering. Yet the scientific rewards would be immense, revealing how ice giants form, evolve, and function. Uranus is a world of mysteries. Its sideways rotation, its offset magnetic field, its lack of internal heat, and its subtle but dynamic atmosphere all pose questions that we do not fully understand. It is a reminder that even within our own solar system, there are worlds that defy easy explanation, that challenge our theories, and that await future exploration. As we leave Uranus and journey to the edge of the classical solar system, we encounter the last of the major planets, Neptune, a world similar to Uranus in many ways but with striking differences, a planet of powerful winds, massive storms, and a captured moon that may be a dwarf planet in its own right. Chapter 10. Neptune, the windiest world. Neptune is the eighth and outermost planet in the solar system, orbiting at an average distance of about 4.5 billion kilometers from the Sun, 30 times Earth's distance. It is slightly smaller than Uranus, with a diameter of about 49,500 kilometers, but it is more massive, containing about 17 times Earth's mass compared to Uranus's 14.5. Neptune takes 165 Earth years to complete one orbit around the Sun. Since its discovery in 1846, it has completed only one full orbit plus a fraction of another. The planet moves slowly against the background stars, taking more than a human lifetime to complete its celestial journey. Like Uranus, Neptune is an ice giant, with an interior composed primarily of water, methane, and ammonia ices surrounding a rocky core. But Neptune is denser than Uranus, suggesting either a larger core or a more compressed interior. The upper atmosphere is composed of hydrogen and helium, with traces of methane that give Neptune its distinctive deep blue color, more saturated than Uranus's pale blue-green. Neptune appears as a beautiful blue sphere when viewed by spacecraft or through powerful telescopes. But unlike Uranus's relatively featureless appearance, Neptune shows dynamic atmospheric features. There are bright white clouds of methane ice crystals, dark storms, and bands of different shades of blue. Neptune's atmosphere is the most active of any of the giant planets despite being the farthest from the Sun. The most famous feature discovered on Neptune was the Great Dark Spot, observed by Voyager 2 in 1989. This was an anticyclonic storm about the size of Earth, similar in some ways to Jupiter's Great Red Spot. The Great Dark Spot rotated counterclockwise and drifted westward relative to the surrounding atmosphere. White clouds, probably methane ice, formed near the spot, likely created by gas rising and cooling in the storm. However, when the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had disappeared. In its place, a new dark spot had appeared in Neptune's northern hemisphere. This suggests that Neptune's storms are not as long-lived as Jupiter's Great Red Spot. They form, persist for a few years, and then dissipate, only to be replaced by new storms elsewhere. Neptune has the strongest winds in the solar system, with speeds reaching up to 2,100 kilometers per hour, faster than the speed of sound in Earth's atmosphere. These winds blow westward in Neptune's upper atmosphere, opposite to the planet's rotation. Why Neptune has such powerful winds when it receives so little energy from the Sun is one of the mysteries of planetary science. The answer may lie in Neptune's internal heat. Unlike Uranus, Neptune radiates significantly more heat than it receives from the Sun, about 2.6 times as much. This internal heat must come from gravitational contraction, the planet slowly shrinking and converting gravitational potential energy to heat, and possibly from other processes like the differentiation of materials in the interior or chemical reactions. This internal heat drives convection in Neptune's atmosphere and interior, creating rising and sinking currents that contribute to the powerful winds. The mechanism is complex and not fully understood, involving the interaction between the planet's rotation, the internal heat flow, and the atmospheric composition. But the result is a planet with more vigorous weather than any other, despite being in the cold, dark outer reaches of the solar system. Neptune has a magnetic field, stronger than Uranus's but still much weaker than Jupiter's or Saturn's. Like Uranus, Neptune's magnetic field is offset from the planet's center and tilted significantly from the rotation axis, about 47 degrees. This similarity suggests that both ice giants generate their magnetic fields in shells of conductive material at mid-depths, rather than in a core. The offset and tilt of the magnetic field cause it to vary significantly as Neptune rotates, creating complex interactions with the solar wind. Neptune has auroras, created when charged particles from the solar wind follow magnetic field lines and strike the upper atmosphere. But because the magnetic field is tilted and offset, the auroras can appear at unusual locations, not just near the poles. Neptune has a faint ring system, discovered in the 1980s through ground-based observations and confirmed by Voyager 2. The rings are dark and contain small particles, possibly created by micrometeorite impacts on Neptune's small inner moons. One of the rings, the Adam's ring, has unusual clumps of material called arcs, which are confined by gravitational resonances with the moon Galatea. Neptune has 16 known moons. Most are small, but one is extraordinary. Tritown, the seventh largest moon in the solar system. Tritown is about 2,700 kilometers in diameter, larger than Pluto, and it orbits Neptune in a retrograde direction, opposite to the planet's rotation. This retrograde orbit is strong evidence that Tritown did not form alongside Neptune, but was captured from the Kuiper belt. Tritown is a fascinating world. Voyager 2 revealed a surface of frozen nitrogen, with polar caps of nitrogen and methane ice. The surface has few craters, indicating recent geological activity. There are strange features like cantaloupe terrain, a rough surface resembling the skin of a melon, and long, dark streaks created by nitrogen geysers erupting through the ice. These geysers were one of Voyager's most surprising discoveries. Despite surface temperatures of -235 degrees Celsius, some of the coldest in the solar system, Tritown has active geysers. Sunlight warms nitrogen ice just beneath the surface, causing it to sublimate and build up pressure until it erupts, shooting dark material, possibly organic compounds, several kilometers into Triton's thin atmosphere. Winds then carry this material downwind, creating the dark streaks visible from space. Tritown is slowly spiraling inward toward Neptune due to tidal forces. Its retrograde orbit means that tidal interactions remove energy from the orbit rather than adding it, as happens with most moons. In 1 to 3 billion years, Tritown will cross Neptune's Roche limit and be torn apart by tidal forces, potentially creating a spectacular ring system around Neptune that could rival or exceed Saturn's rings. Neptune was not discovered through direct observation, but through mathematical prediction. In the early 1800s, astronomers noticed that Uranus was not following its predicted orbit. Small deviations suggested that another planet beyond Uranus was perturbing its motion. Urbain Leverrier in France and John Couch Adams in England independently calculated where this planet should be, and in 1846, Johann Galle at the Berlin Observatory found Neptune within 1 degree of the predicted position. This discovery was a triumph of mathematical physics, demonstrating that Newton's laws of gravity could predict the existence of unseen worlds based solely on their gravitational effects. It also doubled the known size of the solar system once again, revealing that there were worlds in the cold, dark outer reaches that no human had imagined existed. Neptune has been visited by only one spacecraft, Voyager 2, which flew past in August 1989. Voyager revealed Neptune's storms, rings, and moons, measured the magnetic field, and captured stunning images of this distant blue world. Since then, Neptune has been observed by telescopes, including Hubble, which has tracked changes in the atmosphere and discovered new storms. Proposed missions to Neptune are under consideration, but the challenges are even greater than for Uranus. The journey takes over 12 years, and the mission must be carefully designed to withstand the cold and operate far from the sun where solar panels provide little power. A nuclear power source would be necessary, adding complexity and cost. But the scientific rewards would be transformative, revealing the secrets of ice giants and their moons. Neptune is a world of extremes. It has the fastest winds, some of the coldest temperatures, and a captured moon with active geysers. It is the outermost major planet, marking the edge of the classical solar system. Beyond Neptune lies a vast region of icy bodies, the Kuiper Belt, and beyond that, the Oort cloud, a sphere of comets extending halfway to the nearest star. As we leave Neptune and venture into the outer reaches of the solar system, we leave behind the realm of planets and enter the realm of small icy worlds, dwarf planets, and comets. We travel now to the edge of the sun's gravitational influence, to the frontier where the solar system fades into the darkness of interstellar space. Chapter 11. Beyond Neptune, the Outer Reaches. Beyond Neptune lies a vast region of space filled with icy bodies, remnants of the solar system's formation that never coalesced into planets. This is the Kuiper Belt, a disc-shaped region extending from about 30 astronomical units, just beyond Neptune's orbit, to about 50 astronomical units from the Sun. It is home to thousands of known objects, and likely millions more too small or distant to have been detected. The Kuiper Belt is similar to the Asteroid Belt, but far larger and more massive. The objects here are primarily composed of frozen water, methane, ammonia, and other volatiles, with rock mixed in. They are the building blocks of the outer solar system, preserved in cold storage for over 4 billion years. The most famous resident of the Kuiper Belt is Pluto, discovered in 1930 by Clyde Tombaugh. For 76 years, Pluto was considered the 9th planet, the outermost world in the solar system. But discoveries in the early 21st century revealed many similar objects in the Kuiper Belt, some even larger than Pluto, leading astronomers to reclassify Pluto as a dwarf planet in 2006. Pluto is a world of surprising complexity. It orbits the Sun every 248 years at an average distance of about 39 astronomical units, though its orbit is eccentric enough that it sometimes comes closer to the Sun than Neptune. Pluto is about 2,370 kilometers in diameter, smaller than Earth's moon, but it is large enough to have pulled itself into a spherical shape under its own gravity. Pluto has 5 known moons. The largest, Charon, is about half Pluto's diameter, making the Pluto-Charon system more like a double planet than a planet and moon. Charon is so large relative to Pluto that the two orbit a common center of mass located between them, above Pluto's surface. The two are tidally locked, always showing the same face to each other as they orbit every 6.4 days. In July 2015, the New Horizons spacecraft flew past Pluto, providing the first close-up images of this distant world. What it revealed astonished scientists. Pluto is not a dead, cratered world but a geologically active planet with a diverse surface. There are towering mountains of water ice, rising several kilometers high. There are vast plains of frozen nitrogen, smooth and crater-free, indicating recent resurfacing. The most iconic feature is Tambor Regio, a heart-shaped region of bright material on Pluto's surface. The western lobe of the heart, called Sputnik Planitia, is a plain of nitrogen ice that appears to be actively convecting, with warmer ice rising from below and cooler ice sinking, creating a pattern of polygonal cells. This suggests that Pluto has internal heat, perhaps from radioactive decay or from tidal heating when Charon's orbit was more eccentric. Pluto has a thin atmosphere, primarily nitrogen with traces of methane and carbon monoxide. The atmosphere is tenuous, with a surface pressure about 100,000 times less than Earth's. As Pluto moves away from the Sun in its elliptical orbit, the atmosphere freezes and falls to the surface as snow. When Pluto approaches the Sun, the ice sublimes, and the atmosphere returns. New Horizons observed haze layers in the atmosphere, created by photochemical reactions forming complex hydrocarbons. Charon, Pluto's largest moon, is also geologically diverse. It has a dark polar region, nicknamed Mordor, covered with reddish organic material possibly transferred from Pluto's atmosphere. It has canyons and cliffs, evidence of tectonic activity, and a relatively smooth southern hemisphere with fewer craters, suggesting resurfacing in the past. Beyond Pluto lie other dwarf planets. Eris, discovered in 2005, is slightly smaller than Pluto but more massive, with a diameter of about 2,326 kilometers. It orbits at about 68 astronomical units in a highly elliptical orbit that takes 558 years to complete. Eris's discovery, along with other large Kuiper Belt objects, prompted the reclassification of Pluto as a dwarf planet. Makemake and Haumea are other dwarf planets in the Kuiper Belt. Makemake is about 1,430 kilometers in diameter and has one known moon. Haumea is peculiar, shaped like an elongated ellipsoid due to its rapid rotation, spinning once every 4 hours. This rapid spin was likely caused by a collision that shattered Haumea, creating several smaller objects that now orbit the Sun nearby. Beyond the main Kuiper Belt lies the scattered disk, a region of objects with highly elliptical and inclined orbits, likely scattered outward by gravitational interactions with Neptune during the Solar System's early history. Eris is a member of the scattered disk. So is Sedna, a distant object that never comes closer than 76 astronomical units from the Sun and reaches over 900 astronomical units at its farthest point. Sedna's orbit suggests it may belong to the inner Oort cloud, a region between the scattered disk and the more distant Oort cloud proper. The Oort cloud is a vast spherical shell of comets extending from about 2,000 to 100,000 astronomical units, perhaps even farther. It may contain trillions of comets, though they are so distant and so faint that only a few in the inner Oort cloud have been detected directly. The Oort cloud is the source of long-period comets, comets with orbital periods of hundreds or thousands of years. Occasionally, a passing star or tidal forces from the galaxy perturb an Oort cloud comet, sending it plunging into the inner solar system. As it approaches the Sun, ice sublimes, creating the characteristic coma and tail that make comets spectacular objects. Beyond the Oort cloud, at about 122 astronomical units, lies the heliopause, the boundary where the solar wind meets the interstellar medium. The Sun's influence, in the form of its solar wind and magnetic field, extends to this boundary, creating a bubble called the heliosphere. Beyond the heliopause is interstellar space, the region between stars. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Both spacecraft are still functioning, sending back data about the interstellar medium, though their power is slowly fading and they will eventually fall silent. The solar system does not end at the heliopause. The Sun's gravity extends far beyond, dominating the orbits of Oort cloud comets. The edge of the Sun's gravitational influence is roughly halfway to the nearest star, about 2 light-years away. Beyond that, other stars dominate, and we are truly in interstellar space. There is speculation about a Planet 9, a hypothetical planet far beyond Neptune. Certain Kuiper belt objects have orbits that cluster in a peculiar way, suggesting they may be influenced by an unseen massive planet. If Planet 9 exists, it would be several times Earth's mass and orbit at several hundred astronomical units. Searches are ongoing, but so far, no such planet has been found. The outer reaches of the solar system are a frontier, a region we are just beginning to explore. Most of what we know comes from ground-based telescopes and a single flyby by New Horizons. Future missions could visit other Kuiper belt objects, explore the scattered disk, or even send a probe to the inner Oort cloud. Each discovery reveals more about the solar system's formation and evolution. These distant, icy worlds are time capsules, preserving conditions from the solar system's infancy. They have been frozen for over 4 billion years, little changed since the planets formed. By studying them, we learn about the raw materials that built the planets, the processes that shaped the solar system, and the history of the Sun's neighborhood. As we complete our journey through the solar system, from scorched Mercury to the frozen Kuiper belt, we carry with us a sense of the diversity and complexity of the worlds that orbit our Sun. Each planet, each moon, each asteroid and comet has its own story, shaped by its position, its composition, and its history. Together, they form a system, interconnected by gravity, sharing a common origin, evolving over billions of years. Let us now reflect on this journey, on what we have learned, and on our place among these worlds. Chapter 12. Our Cosmic Neighborhood. We have traveled through the solar system, visiting 8 planets, countless moons, asteroid belts, and the icy frontier beyond Neptune. We have seen scorched deserts and frozen plains, towering volcanoes and massive storms, thin atmospheres and crushing pressures. We have encountered worlds of incredible diversity, each shaped by unique circumstances, each telling part of the story of how planetary systems form and evolve. What have we learned from this journey? Perhaps most fundamentally, we have learned that planets are not just points of light in the sky, but worlds as real and complex as Earth. Each has geology, weather, and a history. Each has been shaped by the same physical laws that govern our own world, yet each is unique, a product of its distance from the Sun, its size, its composition, and chance events like impacts or interactions with other bodies. We have learned that the inner solar system is dominated by small, rocky worlds with solid surfaces. Mercury, Venus, Earth, and Mars are all terrestrial planets, but their fates diverged. Mercury lost its atmosphere and became a scorched, airless world. Venus experienced a runaway greenhouse effect and became a hellish inferno. Earth found a balance, with liquid water and life. Mars lost its atmosphere and became a cold desert, though it may once have been warmer and wetter. These different outcomes teach us about planetary habitability. Distance from the Sun matters, but so does size, which affects how long a planet retains internal heat and whether it can maintain a magnetic field. Atmosphere matters, providing greenhouse warming, but also potentially trapping heat in a runaway effect. And chance matters, the random events like impacts or volcanic eruptions that can alter a planet's trajectory. We have learned that the outer solar system is dominated by giant planets, worlds so massive they captured vast atmospheres of hydrogen and helium, or in the case of Uranus and Neptune, accumulated large amounts of ices. These giants have no solid surfaces to stand on. They are fluid worlds, with layered interiors of gas, liquid, and exotic states of matter we barely understand. Jupiter is the king, massive and powerful, with storms larger than Earth and a magnetic field extending millions of kilometers. Saturn is the jewel, adorned with magnificent rings that may be temporary on cosmic timescales. Uranus is the oddity, tilted on its side, with a cold atmosphere and mysterious lack of internal heat. And Neptune is the windiest, with powerful storms and a captured moon that may one day be torn apart to form rings. These giant planets have systems of moons that rival the inner planets in complexity. Io, Europa, Ganymede, Callisto, Titan, Enceladus, and many others are worlds unto themselves, some with subsurface oceans, some with active geology, some potentially habitable. Studying the moons teaches us about processes that occur throughout the solar system and beyond. We have learned that the solar system is not static. Planets migrate, moons are captured or torn apart, asteroids collide and break apart. The orbits of objects change over millions of years due to gravitational interactions. The solar system today is not the same as it was billions of years ago, and it will continue to evolve in the future. We have learned that the solar system is part of a larger context. The Sun is one of hundreds of billions of stars in the Milky Way galaxy. Many of those stars have planets of their own. We have discovered thousands of exoplanets around other stars, some similar to planets in our solar system, others unlike anything we see here. The diversity of exoplanets suggests that planetary systems come in many configurations, shaped by the conditions in their protoplanetary disks and by their subsequent evolution. By studying our own solar system in detail, we learn how to interpret observations of exoplanets. We understand what atmospheres might look like, what geological processes might occur, what conditions might be necessary for habitability. The solar system is our reference, our baseline for understanding planets throughout the galaxy. We have learned that Earth is special, not because it occupies a privileged position, but because it is the only world we know for certain harbors life. The conditions that make Earth habitable, liquid water, a protective atmosphere, a magnetic field, a stable climate, are the result of many factors aligning just right. Venus shows us what happens when the greenhouse effect runs away. Mars shows us what happens when a planet loses its atmosphere. Earth exists in a narrow range of conditions where life can thrive. Yet the more we explore, the more we find that the ingredients for life are common. Water is abundant in the solar system, locked in ice on Mars, Europa, Enceladus, and countless other worlds. Organic molecules are found in meteorites, on comets, in the atmospheres of Titan and other moons. Energy sources, whether from sunlight, tidal heating, or chemical reactions, exist throughout the solar system. Life may be rare, or it may be common. We do not yet know. But the search continues, in the subsurface oceans of icy moons, in the ancient riverbeds of Mars, and perhaps one day, in the atmospheres of exoplanets around other stars. As we conclude this journey, we should remember that exploration of the solar system is ongoing. Spacecraft are currently orbiting or roving on several worlds. Missions are planned to explore Europa, Titan, Mars, and other targets. Technologies are being developed to enable more ambitious missions, perhaps even human exploration of Mars and the moons of Jupiter and Saturn. The solar system is not just a collection of objects to study. It is our neighborhood, the region of space where humanity may one day expand. Mars is a potential future home for human colonies. The asteroid belt may be mined for resources. The moons of the giant planets may harbor life or may become outposts for future explorers. The solar system is our frontier, our next destination as a spacefaring species. But we should also remember that the solar system is our only home for now, and Earth is the only world we can live on without technological support. The fragility of Earth's habitability, revealed by comparing it with Venus and Mars, reminds us of our responsibility to protect our planet. The thin blue line of the atmosphere, the delicate balance of the climate, the interconnected web of life, all are precious and vulnerable. Carl Sagan, reflecting on an image of Earth taken by Voyager 1 from beyond Neptune, called our world a pale blue dot, a tiny speck in the vastness of space. He wrote, "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we've ever known." As you drift off to sleep, or continue your studies, or simply exist in this moment, perhaps you will look up at the night sky and see the planets differently. Venus, bright and white, a caution about greenhouse gases. Mars, red and steady, a world that may once have been habitable and may one day host humans. Jupiter, brilliant and majestic, the king of planets. Saturn, with rings invisible to the naked eye but magnificent through telescopes. These are not just lights in the sky. They are worlds, each with landscapes and weather, history and mystery. They are part of our cosmic neighborhood, connected to Earth by gravity and by origin. And they are destinations, places we have visited with robots and may one day visit ourselves. The planets remind us that we live in a solar system, orbiting an ordinary star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies. Yet this solar system is ours, our home, our birthplace. The planets are our siblings, formed from the same cloud of gas and dust that created the Sun and Earth. They share our history, and perhaps, they share our future. Rest well, under the light of distant planets. Dream of alien landscapes, of storms larger than Earth, of rings of ice, of moons with hidden oceans. And know that you are part of this cosmic family, a citizen of the solar system, living on one world among many, in the company of the planets. Good night, and may the planets guide your dreams.